Welcome to this tutorial. We want to look at ordinary differential equations. We want to know how we test whether an ordinary differential equation is integrable. Remember, before we start this class, kindly subscribe so that you may be getting every tutorial that we post in this platform. Welcome. The general ODE is given by a following equation. PDX plus QDY plus RDZ equal to 0. So that's the general format or form of a general ordinary differential equations. So that's the general equation for that. So for ODE to be integrable, we need to use the following integrability test. This kind of equation here, we call it integrability. We call it integrability test. We call it integrability test, which is P into bracket partial derivative of Q over this partial derivative of dz, partial derivative of R minus over partial derivative of Y plus Q, and so on like that, as you can see it in your screen. So using this particular equation, you have to get the value of P, as from the general equation we have seen that. We differentiate depending on the equation, and this equation, and therefore we substitute. So our core thing here is to do what? Is to get the value of P, value of Q, value of R, and their derivatives, partial derivatives, respectively. Now let's continue. Let us continue. Now let's look at an example. We have this question here which verify whether the equation is integrable. This equation is integrable. What we have been given is zy dx being equal to zx dy plus y squared dz. Now this is how we do it. We first rearrange this equation so that it takes the general format of a general ODE equation, with P dx plus Q dy plus R dz. So rearranging this equation here, we get this. Now we want to make it a bit simpler and arranged well. We arrange it in this format correctly. So what we do here, we divide by zy squared every part. So we divide this part, and this part, and therefore we get this, and get this, and we get this. Okay, so from the above we see that the values of P, Q, and R can be picked, and therefore we have P being equal to this, Q being equal to this, and R being equal to this. So we get their partial derivatives respectively. So we have that. We have also this. We have this. We have this. And this, as you see them in the screen. Therefore, we substitute respectively. Substituting and solving, we have the following condition being true. Why are we saying it's true? Because this one is giving us the 0 that we wanted. So this equation in our example is integrable. So bye for now, until next time.